we have to write integral from minus infinity to plus infinity and put here probability density of x times x dx. We see that this formula and this formula are quite similar. Here we multiply the value that can be the result of our random variable. We multiply it by the probability density at this value. So, for example, if our probability density looks like this, we will include these values that corresponds to areas for which probability density is large into this integral with larger weights that is given by this coefficient. And for example, these numbers will be included with very small weight according to the value of the probability density function. Let me show an example of calculation of expected value for uniform distribution on a segment. Let x uniformly distributed on a segment from 0 to 1. This thing corresponds to the statement that x has a distribution or probability density function that we discussed before. It is uniform distribution on this segment. Then we know how this probability density looks like. Here is 0, here is 1, and our probability density is this. Now, to find expected value of x, we have to integrate from negative infinity to infinity p of x times x dx. However, p of x is equal to 0 outside of the segment from 0 to 1. So, as previously, we can replace this integral with integral from 0 to 1. And at this interval, the value of p of x is a constant, and it is equal to 1. So, we can replace this p of x by 1 and integrate this function. This integral can be calculated explicitly or geometrically. We can say that if this is x and we have 0 here, 1 here, 1 here, the graph of function x is this thing, and this integral is an area like this one. So this is area of this triangle, and its area is equal to 1/2. So the expected value of this random variable is 1/2, which is quite natural because it is in the middle of the segment. Actually, we can use the idea that we discussed before. If probability density function is symmetric, then the axis of symmetry have to be equal to expected value if it exists. If probability density function is symmetric with respect to axis x equals to x naught, vertical line x equals to x naught, and expected value x exists, then expected value x is equal to x naught. Actually, this integral can be non-existent. We will consider some examples of random variables for which expected value does not exist. It is possible. But in general, we will work mostly with random variables for which expected value exists. Now, we will define variance for continuous random variable. Actually, when we defined expected value, the variance will be defined exactly in the same way as for discrete random variables. Properties of expected value and variance for continuous random variables are very similar to the corresponding properties of discrete random variables. Let us discuss them briefly. First of all, let us define variance for continuous random variables. In fact, the formula that defines variance for continuous random variable is exactly the same as for discrete random variables. Variance of x is expected value of x minus expected value of x squared. Of course, if we know how to calculate expected value, then we can find expected value of this random variable as well. Now let us discuss a little bit properties of expected value and variance. First, expected value of sum of two random variables is sum of expected values. Second, expected value of Cx is equal to C expected value x, where C is a constant. These two properties together are called linearity of expected value. From linear algebraic point of view, expected value is a linear operator from random variables to numbers. These properties directly follows from the corresponding properties of integral. So I will skip the proof here. By the way, expected value of constant is a constant. This is very similar to the corresponding property of discrete random variables, and the proof is obvious. It follows immediately that variance of constant is equal to 0. It is useful to discuss how to find expected value of a random variable that is a function of another random variable. Let x be a random variable and y is f of x. Here f is some function from real numbers to real numbers. Then we can find expected value of y in terms of probability density function of x in the following way. This is integral over whole line f of x times p of x dx, where p of x is probability density function of x. Now let us discuss geometric meaning of variance. Let us consider two probability density functions. This is a probability density function of first random variable and this is probability density function of second random variable. How do you think which probability density function defines random variable with larger variance? We can reasonably expect that variance of y is larger than variance of x, because for x, expected value is somewhere here, and the probability that we find value of x which is far from the expected value, for example here or here, is very small. But for y, we can draw expected value, well, somewhere in the middle, for example here. And now we see that even far from expected value, we have some not so small probability to get the value of random variable y. So we can say that random variable x is more compact and random variable y is more wide, has more wide probability density function. And this gives us some intuition about variance of these variables. So we can write, and this is actually correct, that variance y is larger than variance x. We can make this conclusion because the actual curves that define these two probability density function is rather close to each other, so we can compare them in terms of their wideness. Now let us discuss how probability density function changes when we transform variable. We often need to transform random variables, for example by adding a constant or multiplying random variable by a constant. So it is useful to understand how probability density function changes when we do such a transform. First, let us consider adding a constant. Let x be random variable and c be constant. Then we can consider a new random variable y, which is equals to x plus c. And let us assume that we have probability density function for variable x. What can I say about probability density function of variable y? Let us assume that C is some positive constant. How can we find probability density function of y? We have to consider an event that y lies in some segment. How this event is connected with a similar event for x? Let us check. If x is in some segment from x small to x small plus delta x, then it means that y is in similar segment but shifted by this c. So it is in a segment from x plus c to x plus c plus delta x. So when we do transformation, this segment shifts by adding this constant, and we get a new segment. As these two events occur simultaneously, their probability equals. However, the probability of this event, of getting our random variable x at this segment, is involved in the definition of the value of probability density function of f at this point. In the same way, probability of this event is involved in the definition of probability density function for random variable y. And this is, it defines the value of PDF of y at this point, x plus c. So it means that this point is shifted to this point, because this value of x corresponds to this value of y. In the same way, the whole graph of probability density function is shifted to the right if c is positive, exactly by adding plus c to all x coordinates. So let us draw the new graph. We see that it is a shifted version of this old graph. So adding a constant gives us shifting of probability density function. What about multiplication? Let us assume that this graph is a graph of probability density function for x. What is the probability density function for z? Again, we have to consider two events. As z is equal to cx, this event is equivalent to event that z is in segment cx plus c delta x. This is a segment from x to x plus delta x, and when we multiply both endpoints of this segment to some constant, for example, we can think about constant like 2 or 3, we get a new segment like this one. In contrast of the previous case, the length of the new segment is different from the length of the initial segment. So when we write that we are interested in probability density function of z, we have to write that, for example, PDF of z at point Cx is equal to limit as delta z tends to 0, probability that z is in Cx plus delta z over delta z. And to connect this probability with probability of this event, we have to put delta z to equal to c delta x. Now we can move this c out of the limit sign. We see here probability of this event, and this event is the same as this event. If we replace here this probability by this probability, we will get probability density function of x at point x small. So we see that this is equal 1 over c probability density function of x at point x small. In other words, these two probability density functions are related with the following transformation. First, we have to stretch the figure horizontally by multiplying x by c. And second, we have to squeeze the graph vertically by multiplying the value of the function by 1 over c. Now, the new graph looks like the following. The fact that we have to compensate expanding in horizontal direction by contraction in vertical direction preserves the probability of getting somewhere, or in other sense, the area under this curve to be equal to 1. So for this curve, area under the curve is equal to 1 because it is probability density function, and the same holds for the new curve because the expansion in horizontal direction is compensated by contraction in the vertical direction. If we have two random variables and are interested in interaction between them, we have to consider joint distribution and joint probability density function. that x and y are two random variables that are defined on the same probability space. Let us consider joint cumulative distribution function. Joint CDF of x and y is a function of two variables that is equal to probability that x is less than or equal to x small, and at the same time y is less than or equal to y small. To visualize values of two random variables, let us use Cartesian plane. We have two axes, x-axis and y-axis, and random variable x takes values on this x-axis, and random variable y takes values on y-axis, so their pair is denoted by some point on this Cartesian plane. Now let us consider segment here from x0 to x0 plus delta x, and some segment here y0 plus delta y. And let us consider an event that x is in segment from x0 to x0 plus delta x, and at the same time y is in segment y0 plus delta y. It means that x coordinate of the point is here and y coordinate of the point is here, and so the point itself lies somewhere in small rectangle that looks like this one. Now, probability density function of x and y is a function of two variables, x small and y small. Let me draw node here, which is defined as a limit as delta x tends to 0 and delta y tends to 0. And we are interested in the probability of getting into this rectangle, but again, as delta x becomes smaller and delta y becomes smaller, this rectangle becomes smaller, and the probability of getting there becomes smaller. So we are interested in the relation between this probability and the area of this rectangle, and this area is delta x times delta y. So we have a ratio here, and in numerator we have probability of this event, and in the denominator we have area of this rectangle, which is delta x times delta y. This is a joint probability density function of two variables x and y. The function of two variables can be visualized either by three-dimensional graph or by its level curves. Let us use level curves to draw how this probability density function can look like. It is possible, for example, that in this area values of probability density function are large, like greater than 2. In this area they are between 1 and 2, and in this area they are between 1 and 1/2, and here they are less than 1/2. It means that it is more probable to have a point that is here than in similar rectangle somewhere here. So probability density function gives us information about how likely is to have a values of our random variables that together gives us a point near some particular point. So if we will sample from the pair of random variables which probability density function looks like this one, we will get more often points somewhere here, a little bit less often points somewhere here, even less points somewhere here, and almost no points somewhere here. So this is a picture that we can obtain when we generate values from the pair of random variables that we consider. Now, like in discrete case, we can consider marginal distribution. So if we have probability density function of a pair of two variables, x and y, how can we get probability density function of one variable, for example x? In discrete case, we had to consider a sum over all possible values of the other variable, in this case y. In continuous case, we have to replace summation by integration. So we have marginal probability which is defined like this. PDF of random variable x at some point x small is equal to integral of the joint probability, joint density function by dy. Here we have from negative infinity to plus infinity. Geometrically, that means that we fix some value of x, for example this value, and we want to find probability density function of random variable x capital at this point. In this case, we have to draw a straight line like this, and over this straight line our joint probability is a function of one variable, y. The integral of this function gives you the value of probability density function of x at this point. When you change this point, you change this line, and you get different values. This is very close to what we did in discrete random variables. As I said, we just only have to change probabilities to probability density functions and summation by integration. In the same way, we can define probability density function for y if we know joint probability. We just have to swap x and y here and integrate over x. Thus, as you see, joint probability density functions for a pair of random variable is a notion that is very similar to joint probability of discrete random variables. important case is when two random variables are independent of each other. It means, as in discrete case, that knowledge of value of one of these variables gives you no new information about the possible values and their probabilities of another variable. We can state it mathematically in different ways. First of all, we can discuss it in terms of cumulative distribution functions. In this case, we can say that x and y are independent if their cumulative distribution function can be factored as a product of two functions. This is in agreement with the idea of independence of the events that involves the corresponding random variables. For example, let us recall that cumulative distribution function is defined as a probability of the following event. And these two cumulative distribution functions are probabilities of the following events. So, we see here that we have two events. This one, x is less than or equal to x, and this one, the same with y. And here is their intersection. And this equality says that the probability of this intersection is equal to product of these probabilities. It means that these two events are independent of each other. So in other sense, it means that if we know something about the variable x, then it gives us no new information about the variable y. If this relation is held for all possible values of x small and y small, then we say that these two random variables are independent. Another way to define independence is to consider probability density function. Their relation is very similar. Probability density function of x and y, joint probability, have to be equal to probability density function of x times probability density function of y. Actually, this relation follows immediately from the relation like this about the probabilities of some event that involves the condition that value of random variable lies inside some segment or inside some ray, and so on. So this is alternative way to define or to check independence of two random variables if they have probability density functions. Now let us discuss correlation and covariance, which is closely related to independence. Just like in case of discrete random variables, covariance is defined in the following way. Covariance of two variables x and y is expected value of x minus expected value of x times y minus expected value of y. And correlation is defined as a fraction which numerator is equal to covariance, and in the denominator we have square root of variance x times variance y. So like in discrete random variables, if x and y are independent, then their covariance and correlation equals to 0. Again, like in discrete case, the inverse is not true. Let us now discuss a little bit what does it mean that correlation between x and y equals to 0 or to 1. Again, like in discrete case, covariance is related to the formula that gives us variance of sum of two random variables. It immediately follows that if two random variables are non-correlated, meaning that the covariance equals to 0, then variance of sum equals to sum of variances. This fact is very important, and we will use it later when we will discuss law of large numbers and central limit theorem. We discussed discrete random variables that can take only finite or countable number of values with some non-zero probabilities, and continuous random variables that have probability density function. However, it is possible to consider random variables that are neither discrete nor continuous. Sometimes these random variables can be useful for statistical modeling. So let us discuss them in brief. We begin with a continuous random variable which is distributed according to a normal distribution. So the probability density function of standard normal distribution looks like this. As you can see, this random variable can take either positive or negative values. However, let us assume that we have a new random variable that is equals to this random variable, but only for positive numbers. For negative numbers, the value of our new random variable is 0. This new random variable can be defined in the following way. Y is maximum of two numbers, 0 and x. This is an example of defining of new random variable as a function of a previous random variable. However, as we will see, not every function will give us new variable that has probability density function. Indeed, let us ask what is the probability that y equals to 0. Y equals to 0 if x is less than or equals to 0. So this probability is equal to probability that x is less than or equal to 0. And this probability equals to 1/2 due to symmetry of the picture. It is easy to guess that if this probability density function is symmetric, then the probability of left half is the same as the probability of right half, and the sum of these two probabilities have to give 1. So both halves has probability 1/2. So this probability is 1/2. This means that this random variable y cannot have probability density function defined at this point 0. Indeed, if we try to find probability density function of y at point 0, we have to consider a limit for delta y tending to 0 of probability that y lies in segment from 0 to delta y over delta y. In the numerator, we have this probability, and this probability is greater than or equal to the probability that y equals to 0. However, this probability is 1/2. So it means that the numerator is greater than or equals to 1/2. At the same time, denominator tends to 0, so it is arbitrarily small. If you divide some value which is bounded from below by some value that is arbitrarily small, you have arbitrarily large value. So this limit is infinity. It means that probability density function is not defined at 0. On the other hand, if we consider some segment here at positive semi-axis, then here our random variable y coincides with random variable x, and probability that y is inside this segment, for example from x0 to x0 plus delta x, is the same as a similar probability for x. This holds if x not positive. So we are somewhere here. It means that for this part of the picture, we can define probability density function for y. And this probability density function will be the same as for x. So it will be a half of standard normal distribution, the right half. We see that, for example, probability of any point here that are greater than 0 is 0, as it goes for random variables with probability density function. So we have a kind of hybrid random variable that on one hand behaves like a discrete random variable, and on the other hand it behaves for different values, it behaves like a continuous random variable. So we cannot define probability density function for random variable y. However, we can define cumulative distribution function. For negative values of y small, we see that y capital cannot take values that are less than y small. So it means that for all negative values here, the value of this CDF equals to 0. This goes up to 0, but at 0, CDF have a jump. Indeed, CDF y at 0 equals to probability that y is less than or equal to 0, and as y cannot take negative values, this is the same as probability that y equals to 0, and this probability, according to previous, is equal to 1/2. So here we have a jump to the level 1/2. After the jump, the probability that we have can be calculated in the same way. For example, if we have some point y naught here, then CDF y at point y naught is equal to probability that y is less than or equal to y naught, and this probability can be splitted into two probabilities. Either y equals to 0 or y is greater than 0 but less than or equal to y naught. And this probability is defined by probability density function, by the integral from here, from 0 to y naught, by this integral. So the corresponding CDF looks like this one. Thus we see that we can define this a little bit strange random variable by defining its cumulative distribution function. Previously, we discussed how to generate discrete random variables like binomial or Poisson. Now, let us generate some continuous random variables like uniform. Again, we can use special functions from NumPy random or SciPy stats to do it. For example, let us begin with NumPy random and import uniform. Uniform is a random number generator that uses a uniform distribution on some segment. Again, we can check how it works. We can define the endpoints of the segment. For example, I want to generate some random numbers with uniform distribution on segment from -2 to +2. So I have to specify low and high limits. And now you see that the numbers that we have are just some real numbers in this interval. As usual, we can specify size argument to generate samples from this random variable. And to visualize the results of this generation, we can use histograms. Let me show you how histograms work in Python. We have to use matplotlib pyplot again. Some magic commands here. To study how histograms work, let us consider some artificial data set. For example, I have data 1, 1.2, 4.1, 4.2, 4.3, 5. And I can use hist to visualize this data set. Let me use different number of bins to make the picture more explicit. You see here two rectangles. First rectangle is over this segment, and its height corresponds to the number of points that lie inside this segment. Let us draw these points as well. I can use pltplot to do it. So x coordinates of our points will be these numbers that is in list data. And I will put some fixed y coordinate, for example 0.1 times length of data. So every point will have the same y coordinate. And let us add some markers here. So you see that over this segment we have 2 points, and over this segment we have 4 points. So this rectangle have height 2, and this rectangle have height 4. We can also add option density equals to true. After this option, we rescaled the vertical axis in such a way that the area of this picture equals to 1. So this picture resembles the probability density function. Now we can see how this picture will change when we change our data set. For example, let us move this point here. I have to replace 1.2 into 3 and start this comment again. And you see that now we have 2 rectangles of the same height here and here. And this rectangle is higher proportionally to the number of points. Now we can use this histogram to study the samples that was gathered from this uniform function. Now we see that this histogram does not resemble the probability density function as expected, but this is due to low size of our sample. Let us increase sample size a little bit. This is much better. Let us increase it more and more. Let us add density equals to true here. Now, from this histogram, we see that the probability of getting our random variable on every segment is more or less the same, provided that the length of these segments is the same. We see that the heights of corresponding rectangles are more or less equal, at least approximately. Now let us draw on the same graph the corresponding probability density function. To get this function, we can use corresponding object from SciPy stats package. I will do it in the following way. I will import SciPy stats. And now I will use SciPy stats uniform to avoid collision with this function uniform, which is from NumPy library. So to create the corresponding object, we have to specify the parameters of the distribution, and in contrast with this function uniform, when we specify left and right endpoints of a segment, here we specify left endpoint of a segment and length of this segment. Now we can use this object to find, for example, probability density function at arbitrary point. For example, at point 1.2, the value of probability density function is 1/4, which is correct because the length of our segment is 4. Now let us draw the graph of this function. To do so, we import NumPy. Again, to plot a graph of a function, we have to specify a set of points at which the corresponding values of a function will be found, and these points will be shown on the graph. It is easy to use NumPy linspace function to create the corresponding set of x values. Let us assume that we start from -3 and end at 3, and we need 100 points. Now x is just this list of values from -3 to 3, and then I will plot x PDF of x small, and this is actually the graph that we discussed at the lectures, and we can draw this graph on the same picture as this histogram. So let me just copy paste it here. Now we see that our histogram actually approximates the corresponding probability density function. And the larger sample size, the better approximation is. We can use a similar technique to analyze any probability distribution. For example, one of the most important distribution for us is normal distribution. And of course, Python can generate normally distributed random variables as well. We will discuss it later. When you sample from some random variable using Python, these samples are independent to each other. But it is also possible to generate dependent random variables. For example, correlated normal random variables. This can be done using a special function NumPy random multivariate normal. Let us use this function to see how correlation affects the joint distribution of random variables. Again, I need to draw pictures. And I need NumPy as NP. Now we will use multivariate normal to generate correlated normally distributed random variables. First of all, let us define several variables. Variance 1 equals to 1, variance 2 equals to 1, covariance equals to 0.5. Then we have to create covariance matrix. That is the following matrix. We have variance 1 and covariance here, and covariance and variance 2 here. So you see that we have variances of our random variables on the diagonal of this matrix and covariance on the off-diagonal elements. So now we can use this multivariate normal. We have to specify expected values of each random variable, for example 0, 0, and then covariance matrix. And I will also specify size of sample. Let us begin with 10. Now you see that this function generated two-dimensional array. So it is basically a table, and the first column of this table is the value of first random variable, and the second column is the second random variable. Now to visualize these random variables and a relation between them, we want to use scatter plot. So I just say that this is our data, and then use plt scatter to visualize this data. To get first column of this matrix, I have to use the following slice. Here is the index that we use, and this column is just a slice for from start to end, and this slide corresponds to the values of index that corresponds to row. So this index basically says that we want to get all elements from all rows, but for zeros column of our two-dimensional NumPy array. So this is the values of the first variable that we created, and this is values of the second variable. This figure is not very informative. Let us increase sample size. It is much better. Let me increase covariance. In fact, we use variables which variances are equal to 1. In this case, covariance equals to correlation. So let us increase it, for example, to 0.9 and redraw the picture. Now we see that there is a clear correlation between our random variables. because we see that, for example, if the first random variable is large, somewhere here, at the same time, value of second random variable is also large. At least in our samples, we see only rather high values of the second random variable. And if first random variable is small, like here, -3, then the value of second random variable is also small. This means that we have a correlation. Let us play a little bit with this covariance or correlation parameter. For example, if I decrease it to 0, we get a picture like this. Just by looking at this picture, we see almost no correlation because this cloud of point is more or less symmetric. And if we put covariance to 0, we see that there is no correlation here. If we know that the value of one variable is large, like near 3, we have no new information about the value of another variable. We can also make this covariance negative. For example, -0.5. You see slight negative correlation in this case. Negative means that higher values of first variable corresponds to lower values of the second variable. And we can decrease it further and get this picture. And we can put here -1 to get this picture. In this case, we have perfect linear relationship between these two random variables. So in this case, if I know that first random variable has value 2, then I know for sure that the second random variable has the value -2. And we can also put 1 here and get this line. Of course, we can play a little bit with these variances as well. For example, I can put variance of the second variable to be 4, and you see that the range of the second variable is increased, but the covariance that is equal to 1 does not give us this perfect correlation. To get perfect correlation, we have to increase covariance to 2, and in this case correlation again equals to 1. In this case we used this multivariate normal function to get correlated normal random variables, but we can achieve similar result without using of this function. Let us consider another example. How can we generate some correlated random variables? We can do it in the following way. First, we generate values of first random variable x. We will just use standard normal distribution for simplicity. Then we say that our second random variable y will be generated in the following way. It equals to x plus some noise, plus some shifts that is also random variable. I will denote this random variable by epsilon. And I have to generate the corresponding values of epsilon here. And let us assume that it is also normal random variable. Now let us draw the corresponding scatter plot. You see that at this picture these random variables are correlated, and in fact we can change the corresponding correlation coefficient by introducing some coefficients, for example for epsilon. if I put a small number here, the relation between y and x would become stronger because these random shifts will be of less magnitude. So we see that these random variables are better correlated than before. And we can change this coefficient and get small correlation or large correlation. In this case, the correlation is very small, but as you can find, it is anyway positive, but it is almost impossible to see the positiveness of the corresponding correlation from the data. This model is important because when we will study linear regression, we will use this kind of relation between two random variables when we introduce this linear regression model. We start learning statistics. Statistics deals with data, and data is usually represented in a form of table. In this table we have several rows. There are shown only 4 rows, but we can imagine much more rows, and several columns. And each row, which is called observation, for example, can correspond to some participant of a study or to some other kind of observation. And each column represents some variable, some property of these observations. In machine learning, variables are also called features. This table is very large. And to get some idea about our data, we can use different summarization and visualization techniques. First of all, we will discuss descriptive statistics. The word statistic here does not mean the branch of science. It means just some number that is associated with our data. For example, consider a column with age. We can be interested in the average age of participants of our study. To find this average, we can just use arithmetic mean of all numbers that we have in column age in our dataset. And we can conclude that average age is 31. But this information is not enough to get reasonable understanding of our data. For example, we may be interested also in measures of statistical dispersion, of measures of how different our values are. All of them are near the average value, or there is a wide range of values. To answer this question, we can use another descriptive statistics, so-called standard deviation. We can find a standard deviation by formulas that we will discuss and get that it is 22. After that, we can report, for example, that the age of our participants is 31 plus or minus 22. It gives information about the average value, and it gives information about an average deviation from this average value, so the range of the participants of our study. These two are examples of descriptive statistics. Another way to get information about the data is visualization. For example, we can draw a histogram of our variable age, and using this histogram we can get an idea of the distribution of ages of the participants of our study. And we also can communicate the same thing to somebody else. Visualizations are important technique in understanding of the data.
at this week. First of all, we will discuss the connection between statistics and probability theory. Connection between random variables that we studied in probability theory and our data. We will discuss different kinds of data and different kinds of descriptive statistics. Descriptive statistics are measures of central tendency, which measure, in some sense, typical object in our data set. There are mean, median, mode, and measures of statistical dispersion like variance, standard deviation, or interquartile range. We will also discuss quartiles themselves and the generalization quantiles. We will discuss how to visualize distribution of continuous and categorical variables using histograms and bar plots. And finally, we will discuss how to use Python to find descriptive statistics and visualize data.
Statistics is a science that allows us to make conclusions about some real-world phenomena or processes or systems using some data that are extracted from this real world. However, these real-world phenomena can be very complex. And to simplify their study, we replace them with, in a sense, simpler mathematical models. Statistics involves some kind of mathematical modeling. Let us discuss now the very general framework of models in statistics. Let us assume that we study, for example, customers of some shop. In this case, it is possible that we have data about these customers, and this data is presented in a form of a table. Columns of this table represent some properties or features of our customers, something like age or income or number of children, and so on. And every row of this table represents one customer. For example, it is possible that we have a 70-year-old customer with income 1,500 and no children. And it is possible that we have another customer, 35-year-old, with income 2,000 and one child, and so on. This is a general form of representation of the data. And there is a terminology that is related to this table. Columns of this table are called variables or features or properties or something like this. Usually it is features in machine learning and variables in statistics. So columns are called variables or features. And rows of this table are called observations or objects or items. Rows are usually observations or objects. We can rewrite this table using formal mathematical notation. I can rewrite it in a form of a matrix. For example, I can denote these values by letter x with some indices. For example, x11, x12, and so on, x1d, this is x21, this is x22, and so on, x2d, and so on, xn1, xn2, xnd. So, if I write this table in the form of this matrix, then it means that I have d features, d columns of this matrix, and n objects and observations, and rows of this matrix. So this matrix is usually called object feature matrix or something like this. You see that I use these upper indices to denote different variables, different columns of this matrix. So do not confuse this upper index with power. It is not x1 to the power d, but it is just x1d. So we have here d features and n observations. We can assume for a moment that all these variables are just real numbers. In fact, as we will discuss soon, it is possible for some variables to be not numeric but of some other kind. For example, variables like gender or country of origin are not numeric. But for a moment, let us assume that all these values are just numbers. So xij is just a real number. In this case, we can consider this matrix either as a collection of rows, and each row is a d-dimensional vector. So we can say that we will denote this by xi, and xi is i's observation, and it is d-dimensional vector. Or we can consider this table as a collection of its columns, and each column is n-dimensional vector. So we can denote it by x with upper index j, and this is n-dimensional vector. We assume that our data is obtained as a result of some random experiment. For example, if we discuss some study that involves some people, then it means that these people that are included in this study are selected from the general population in a somewhat random way. So we have some randomness in this table. And we may assume that each row of this table is a realization of some random variable or system of random variables. And our model is rather simple. We have main assumption that there are several random variables, or better say, a system of random variables that corresponds to variables of our data. We have x1, x2, and so on, xd, a system of random variables. Such that our observations are independent samples from this system. So we can say that our observations x1, x2, and so on, xn are independent and identically distributed with this distribution. with distribution of this system. This means independent and identically distributed. What does it mean on practice that they are independent and identically distributed? It means that we assume that, for example, income of a second person in our study does not depend on the income of the first person in our study. And in the same way, income of the second person does not depend on the age of the first person. So rows are independent of each other. But columns, of course, can be dependent. For example, it is easy to assume that income in some way dependent on age, that these two variables are correlated, for example, because we expect that a person with larger age probably have larger income. So we assume that these variables are independent and they has the same distribution, that all rows of this table is obtained by sampling from the same population of all potential customers or all potential participants of our study. This is our basic model. And the main goal of statistics is to observe this sample or observe this table and make some conclusions about these random variables, about their properties, about their correlations, and some more complicated relations between them. So, to conclude, our goal is to make conclusions on our random variables. This system of random variables is also called a population. It does not mean that we have to study an actual population of some people. It is just a general term that is used to refer to a system of random variables that generated our data, that generated our sample. Now, let us discuss how to study this data, how to describe them. To do so, we have to discuss so-called descriptive statistics. Before we proceed with discussing of descriptive statistics, we have to discuss first what kinds of variables we can meet in the data. First of all, the easiest to deal with type of variable is just a numeric variable. Numeric variable is something that is denoted by a number, for example, income or number of children. Numeric variables can be subdivided into two categories. We can consider real numbers for example, income or for example, weight or something like this. And another option is to consider count, something that is denoted by integer numbers. It is usually denoted by count or integer. For example, number of children. difference between real numbers and integer numbers can be important in some cases when you have to use different models for these different kinds of variables, but sometimes this difference is neglectable. Sometimes it is even possible that we have some column of data and we can represent it either or by real numbers or by integer numbers. For example, a variable like age can be represented and modeled as real numbers because age is basically a real variable if we consider not only the number of full years but also number of months and days and so on. But usually it is considered as integer number. Anyway, numeric variables are in a sense simple. Another option is categorical variables. Categorical variables represents some values that are not numbers, but that are some elements of some fixed sets. For example, we can consider a variable like country of origin, or city of origin, or level of education. These are examples of categorical variables. These categorical variables can also be subdivided into two classes. We can consider ordered categorical variables, for example, level of education. For example, we can consider several levels of education like general education, higher education, college, scientific degree. And we understand that there is an order on the set of all possible values. We understand, for example, that the college education is larger in a sense than general education. And also it is possible that we have categorical variable that does not contain any order on the set of possible values, not ordered. This kind of variables are also called nominal variables. For example, country of origin. And there is a subset of categorical variables that can take only two possible values. These are called binary variables. Sometimes it is useful to consider them too. When we study our data, we want to use mathematical tools that deals generally with numbers. So, if we have some kind of categorical data, we have to transform them into some numeric form first. And this can be done in different ways. Let us assume that I have a variable like country of origin or hometown. Then I want to encode this variable in some numeric way. For example, I have possible values for hometown. For example, in my study, there are only three possible hometowns: Moscow, New York, and London. And I can use the so-called label encoder to encode this variable. In this case, I say that, for example, Moscow is encoded as 0, New York is encoded by 1, and London is encoded by 2. This is called label encoder. Every time I see Moscow, I just replace it with 0. Every time I see New York, I replace it with 1. In this case, I can transform a column that corresponds to this hometown to the column of values 0, 1, 2. This is the simplest possible way how to do it. But sometimes it is not an optimal way. Because when we denote these categorical values by numbers, we introduce some kind of relation between these values. For example, we can make some arithmetic operation with numbers or some comparisons. In this encoding, we see that London is larger than Moscow. In some sense. But we understand that these relations between these numbers are just an artifact of our encoding scheme. Because, for example, we can denote Moscow by number 2 and London by number 0, and these relations will be reversed. And we see that it is just because we changed our mind about this encoding scheme. So for some models of machine learning, this is not a problem. But for some other, like linear regression models, this is a problem because they assume that when they see a number, this number has the appropriate numerical value, numerical meaning. And in this case, we have to introduce another encoding schemes. For example, the very popular one-hot encoding. In one-hot encoding, we associate with our categorical variable, like hometown, several numerical variables, like this. Assume that we have variable hometown, and we introduce new variables. First variable, hometown Moscow. Second variable, hometown New York. And the third variable is hometown London. Then, when we see here in the column hometown, we see Moscow. We put here 1, here 0, and here 0. When we see here New York, we put here 0, here 1, and here 0. And for London, it is the same way. Here 0, and here 1. In this case, there are no such problems, for example, that we compare, in a sense, Moscow and London and make conclusions which is larger in our encoding, because in this case, every value of this variable is encoded not by one number, but by a vector of numbers. And these vectors cannot be compared, just like the initial levels of our categorical variable. This one-hot encoding is extremely popular in machine learning. In statistical settings, it is also useful to consider so-called dummy encoding. Dummy encoding is just the same thing as one-hot encoding, but we remove one of the columns of the transformed data. For example, this column. we can safely remove it, because if we see 0 here and 0 here, we understand that our hometown is not Moscow and not New York, and therefore it has to be London. So in this coding scheme there is some kind of redundancy, and if we remove one column, then we remove this redundancy. For some methods like linear regression, this can be important. Anyway, we have to transform our data in a numeric form before we can proceed with the analysis of this data by machine learning tools. Sometimes these transformations are as simple as we discussed here. Sometimes they use much more sophisticated techniques like word-to-vec or some other embeddings of some complicated objects into vector spaces. Anyway, finally, we have just some numeric values in our data, and we can use a bunch of mathematical tools to process them and analyze them. Now, let us discuss how to summarize the data of different kinds. Assume that we have several observations in our dataset, and we are interested in a particular variable, for example, age. What we are interested in is some value that is, in a sense, a typical value of this variable across our dataset. There are several possible answers to this kind of question, and these answers are called measures of central tendency. Assume that we have some numeric values in our variable. Then the first measure of central tendency, probably the most known, is just average or mean. Let me assume that I have values which will be denoted by x1, x2, and so on, xn. And I will denote these values by letter x. Then average of x, or mean of x, is just an arithmetic average of these numbers. So it is usually denoted by x bar, and it is just a sum of these values divided by the number of these values. This is just an arithmetic average. This is a very known measure of central tendency. Sometimes we say that the average age of our respondents is the following, for example, 35 years. And some reader of our report understands that we consider adults and not children. So this average provides us some useful information about the dataset. But it is not the only possible way to consider this measure of central tendency. Another way is to consider median. What is median? It is easier to explain using some example. Let us assume that my x is a series of numbers like this one.
Let me rearrange this sequence in ascending order. So I just sort these values. In this case, I have 2, then 2, then 3, then 5, then 70. Then I will pick the element that is in the middle of this sorted sequence. This element is called median. If there are even number of elements in our original data set, then there is not one element in the middle, but 2 elements. In this case, median is just an average of these 2 elements in the middle. But it is a rather technical remark. The idea of the median is that it is an element such that the half of elements is larger than median and another half is lower than median. Sometimes it is important to use median and not average. For example, if we discuss incomes, for example, we discuss incomes in some country, and we understand that in this case we have not so many people who has very large incomes, and most of people doesn't have such large incomes. Those people with very large incomes can affect average rather significantly. But for median, if I replace, for example, this number 70 with 70,000, it does not change median in this set at all. So, in a sense, median is a more robust measure of central tendency. It is not sensitive to values that are too large or too small, if we don't have many of these elements. And this is a good property of median when we discuss such thing as, for example, median wage. Also, another advantage of this median is that it can be applied not only to numeric data, but also to ordered categorical data. Because if we have odd number of elements, the only operation that we need to find this median is just to sort these elements. And to sort them, we just have to compare which one is larger. So even if you don't have numeric values, but you have just categorical but ordered values, you can find the median of the corresponding data set. Next, let us discuss a third popular measure of central tendency, which is called mode. Mode is just the most frequent value that we can meet in our dataset. The advantage of mode is that it can be applied to unordered categorical variables, for which even median is not defined, because we cannot compare the corresponding values. For example, if we have some data set that corresponds to variable like hometown, and then our x is something like Moscow, New York, London, again New York, again Moscow, and again New York. In this case, we can find mode of this x, and it is just New York, because New York is the most frequent value in this set.
So mode of X is New York, the most frequent value. Of course, it is possible that there are several most frequent values in the dataset. For example, if I add Moscow into this dataset, then we will have 3 elements with value New York and 3 elements with value Moscow. And both of them will pretend to be called mode of X. In this case, we have to select from these elements in arbitrary way. For example, we can sort the corresponding labels alphabetically and select the first label under this sorting. In this case, it will be Moscow. Mode is defined for any values, for any types of variables, but it is mostly useful for categorical unordered variables with not so much different values. Measures of central tendency describe, in a sense, a typical element of our dataset. But it is also important to understand how far elements of our dataset deviate from this typical value. To do so, we have to consider some other descriptive statistics, for example, variance. Let us proceed to them. Sometimes it is very important to know not only a measure of central tendency, like an average, but also some measure of deviation of our values from this average. Let us consider an example. Assume that you have 2 studies and you have ages of participants of these studies. In the first study, age of participants is the variable that take the following values. For example, 35, 37, 34, 33, and 36. What is the average age of participants in this study? You can find the arithmetic average of these numbers and find that the corresponding average equals to 35. Now let us consider a second study. And again we have age of participants. And these ages are the following: 35, 10, 65, 65. You can again find the average of these numbers. What is the answer? You see that the answer is again 35. But it is clear that these 2 studies are in a sense different. This study is aimed on adult persons around 35 years, plus or minus several years. And this study is aimed not only on adult persons, but also on very young, on children, and some elderly persons are also included. So there is a clear difference between these 2 data sets. And this difference cannot be encoded into the measure of central tendency because the average value here and here is the same. Then we have to use different descriptive tools to distinguish between these two data sets. And the first tool is called sample variance. Let us consider a data set that will be denoted by x, and it contains values x1, x2, and so on, xn. All these things are just numbers. And we can consider x bar, which is just a mean of these numbers. Then sample variance of x, let me denote it by var, is the following thing. It is an average of square of deviance of values of x from their average value. So I have to find a sum for I from 1 to n, xi minus x bar, take a square and divide this sum by n. Due to some statistical reasons that we will discuss later, we can write here instead of n minus 1. In a sense, the variant of this variance formula, where n is replaced with n minus 1, is better than this variant. So this variant is called biased sampled variance. And to make it unbiased, I have to consider another definition. Let me denote it by var plus x, and it is the same formula as here, but I will get n minus 1 here. This is called unbiased sampled variance. As you see, the formula for variance is related to the formula of variance of random variables that we discussed in the course of probability. There is a relation between sample variance and variance of random variables that we probably discuss later. And in the sense of this relation, this formula for variance is better than this one. But I'm not going to details now. Let us consider now another way to encode this variance. Instead of considering this variance, we can take a square root of it and consider the so-called standard deviation. Standard deviation, which is denoted by STD usually, is just a square root of variance. The advantage of standard deviation over variance is that it uses the same units that x itself. For example, if x is age and it is measured in years, then x bar is also measured in years, and the square of this difference is measured in squared years, which is a rather strange unit. And you cannot, for example, make a summation of
years and squared years. It doesn't make sense. So sometimes we need some measure of deviance that is measured in the same units as the value itself. And standard deviation is a good candidate for this. Sample variance and sample standard deviation are not the only possible ways to measure this deviance. Let us consider another approach. Let us return to an approach that we used when we defined median. Consider an example. Let our dataset X contains of the following numbers. For example, 1, 3, 2, 7, 100, 11, 17. First, I have to sort this series of numbers and get the following series. 1, then 2, then 3, then 7, then 11, then 17, then 100. In this sorted series, again, as we did previously, I denote the center, which is median. Now you see that this median splits the dataset into two equal parts, this part and this part. And I can find a median of each part. Here it is this number 2, and here it is this number 17. So this thing is called first quartile, Q1, first quartile. And this value is called third quartile. Median can be also called second quartile. These values, first, second, and third quartile, divide all dataset into four approximately equal parts. This part, this part, this part, and this part. This is why they are called quartiles. Note that the half of our sample is contained between first and third quartiles. So the difference between these third and first quartiles is called interquartile range, abbreviated by IQR, is the difference between third quartile and first quartile. This value, interquartile range, can be used to estimate how far values of our dataset deviates from some element in the middle, in this case from median. You see that if this value is large, much larger than median, and this value is much lower than median, then it means that the deviance is large, and interquartile range will be large. But if all values here are almost equal to median, here a little bit larger and here a little bit smaller, then our deviance will be small,
and interquartile range will be small. Quartiles are defined like median not only for numeric data, but for any ordered categorical data as well, because the only thing that we need to find them is an ability to sort these values. And to sort them, we have to compare them, and in ordered categorical values, we can compare them too. But to find this interquartile range, we have to find this difference, and it involves arithmetic and it involves some numeric values, because otherwise we cannot do this subtraction. Anyway, just like median, interquartile range benefit some kind of robustness. If by some mistake I will replace this 100 with 10,000, it will not affect these quartiles at all. But if I consider variance, we see that if I replace one element with much larger element, it will considerably change the corresponding variance. So quartiles and interquartile range are in a sense more robust tools that can be useful sometimes, for example, if you deal with data with lots of outliers, elements that lie outside of the expected distribution of the data. Now, we discussed measures of central tendency and measures of deviance from the corresponding element in the middle. But sometimes we have to understand our data in more details to get more deep understanding of the data than these values gives us. In this case, we have to study their distributions, and this can be done with the corresponding visualization technique. Let us discuss them. Descriptive statistics that we discussed before, like average or median, and the corresponding deviance measures like standard deviation, give us some information about our data. But if we want to analyze the data, even the one variable, in details, we have to understand something about its distributions. The distribution here means that we want to understand which values are more frequent and which values are less frequent. This can be done by some visualization techniques like histograms and bar plots. Let us discuss them and the difference between them. We begin with numeric and more specifically real variable. It means that in our data we have just a column of numbers, and these numbers can be represented as points on some axis. So this is axis x, and each data point, each observation corresponds to some number that is denoted by a point on this line. For example, we have 0 somewhere here and 1 somewhere here. Then this point is just 1/2. And it is possible to plot all the points on this line to get something like this. If you look at this picture, you see that there are lots of points here and some amount of points here. But this picture is meaningful only if the number of points, a number of elements in your dataset is not too large. Because if there are a lot of points here, you cannot distinguish regions where you have a lot of points and regions where you have small amount of points. So usually people use a different visualization technique which is called histogram. We already met with histograms in probability course. So let me recall briefly how histogram can be constructed. First of all, we divide all range of our data into segments, something like this. And then we plot rectangles over each segment in such a way that the height of the corresponding rectangle is proportional to the number of points in this rectangle. We assume that these segments are equal to each other. So we have 2 points here. Here we have 3 points, so it is a little bit taller. Here we have 1 point, so this rectangle is twice as short as this rectangle. And we have 4 points here, so this rectangle have to be twice as this rectangle have to be twice as large as this rectangle. So this picture allows us to understand in which regions we have a lot of points and in which region we have a smaller amount of points and where we don't have points at all. And this is called histogram. So, histograms are used to represent distributions of numerical variables. What about categorical variables? Let us assume that I have a variable like hometown. And in this variable, I have the following values. This is Moscow, then New York, then London, then again New York, then again London, and then again New York. Now assume that I'm interested in the frequencies of values in this set. So it means that I want to ask a question, which values are frequent and which values are rare. And to answer this question, I can find frequencies of each values. So I just have to count how many times each value appear in this series. And I can draw a table like this. Moscow 1 time, New York 3 times, London 2 times. So this is value and this is frequency. This table effectively summarizes this series of values. For example, if we increase the size of this series, if we add a lot of items here, if the overall number of all possible values will be only limited to these 3 options, Moscow, New York, and London, the size of this table will be the same. We will just increase numbers here. So it is sometimes a very good idea to look at this kind of table
and understand which values are frequent and which are rare. But sometimes we want to visualize this kind of table. And this can be done using a picture which is called bar plot. And it resembles this histogram, but it is quite different from it. So we have to draw some segments that corresponds to each of values here, like here Moscow, here New York, and here London. And then over each of these segments I draw a rectangle which height is proportional to the corresponding frequency here. So for Moscow I draw this rectangle, the height is 1. Here for New York I draw a much taller rectangle, this is height is 3, and for London I draw this rectangle of height 2. And this picture consists of these rectangles, is called bar plot. Now that it is important to distinguish between histograms and bar plots. Because if you want to plot a histogram for this categorical data, then you probably want to do something strange. You need bar plot here. Also, bar plots can be used to draw not categorical variables but count variables. In this case, they are very similar to histograms. But again, the meaning is a little bit different, because for histograms you can select the length of this segment as you find it appropriate. But for bar plot, every rectangle corresponds to exactly one possible value of your variable. So you have to distinguish between these kinds of plots. Now, let us discuss how random variables and their properties are connected to our data and the corresponding descriptive statistics. As we discussed, we assume that our data is a sample from some random variable or system of random variables. So it is important to discuss the relation between properties of samples, like sample average or sample variance, and the corresponding properties of random variables. Let us assume that we have a sample of numeric values like x1, x2, and so on, xn, and these values are sampled from some random variable x capital. I will refer to the collection of these x's as x small. We can consider the relation between properties of x capital, which is a random variable, and properties of this sample. We begin with sample average, sample mean. It is related to the expected value of x capital. As we discussed in the probability, the expected value is, in a sense, an average value of random variable. Due to law of large numbers, when we increase the size of sample, when we increase n, sample average tends to the expected value of the corresponding random variable. A similar relation can be established between sample variance and variance of the random variable x capital. Both sample variance and unbiased sample variance tends to the variance of the random variable x. Both sample variance and unbiased sample variance can be used to estimate variance of the corresponding random variable x capital. Because as n tends to infinity, so the size of the sample becomes very large, both of them tend to the corresponding variance of x capital. But this unbiased variance is a little bit better in some statistical terms than biased variance. Then we can discuss in the same way the standard deviation of sample. Standard deviation is just a square root of the corresponding variance, usually unbiased sample variance. So standard deviation of x tends to the standard deviation of x capital, which is in turn just a square root of variance of x capital. This also usually denoted by sigma with index x capital. By the way, this variable x capital is also usually called a population. So these properties are called properties of population or population statistics. And these properties are called sample statistics. Now, let us discuss median. There is a population median which is related to this sample median. For random variable x, if this random variable is continuous random variable, we can define median in the following way. Median x is such number probability that x is greater than m equals to probability that x is less than m, and both are equal to 1/2. So if we have some distribution that is given by probability density function, something like this one, then the median is a value that divides the area under this curve just by two halves. This is one half and this is another half. So, this sample median corresponds to the corresponding population median, which is defined in this way. By the way, in the same way, we can define not only median, but any value that divide this area under the curve in a certain proportion. These values are called quantiles. Previously, we discussed quartiles, which are just an examples of quantiles. Let me define what is a quantile for random variable. P quantile of x, where p is some number from 0 to 1, is such value xp, which satisfies the following relation. Probability that x is less than xp equals to p. So, for example, if I have some distribution and I'm interested in O.1 quantile, I have to put a point somewhere here, such that the area under this part of the curve is O.1 and the area under the rest of the curve is O.9. We can define quantiles for sample as well. For sample, P quantile is a number xp such that the following holds. Let us consider the part of our sample which is less than xp. So this is xi for all xi that are less than xp. And I want that this number, the number of elements in this set, be approximately equal to p times n, the size of our sample. So it means that, for example, if I'm interested in O.1 quantile, I have to just sort my sample, then divide it into 10 equal parts, and the border of the first part is just x O.1. So this is O.1 quantile. Quantiles sometimes can be useful to describe, for example, the sum of the largest values that belong to our sample or sum of the lowest values. So we see that we have properties of samples and corresponding properties of population, properties of the random variable that used to generate this sample. And in statistics, we use properties of sample to estimate the corresponding properties of population. This is our main goal. We will use statistical tools not only to say that this can be done, but also to quantify possible errors of this estimation. Now let us discuss how to use Python to analyze data. To do so, we will use a well-known library which is called Pandas. Pandas allows us to read a table from some file into a structure which is called data frame. Data frame is just an internal name of a Python object that contains table inside. First of all, I have to import pandas, and this is usually done by import pandas SPD. This allows me to get access to different functions inside pandas model using this short prefix PD. Then let us load some dataset and play with it a little bit. To do so, I will use a dataset which is called adult, and it is based on the results of census in United States, and it contains information about some people and allows us to find some useful insights in this data. I downloaded file adult.csv and placed it to the folder where Jupyter was started. So now I can just load it into pandas using the following command: pd.read.csv, and here is the name of the file. Let us run it. Here df is just a name of my variable that will contain this data frame. df stands for data frame, but it's just my choice. Here I say that I will use function from pandas model, and read.csv is the name of this function. As the name suggests, it just reads some CSV, comma separated values file, and returns my data frame. And now we just look inside this data frame, and here you see the table that contains some information about different persons: their age, where they work, their education, and so on. Here all columns are shown in this window. But it is possible that our data frame is so large, it has so many columns that this command will not show us all the columns. And in this case, we can use the special syntax that allows us to find all columns in dataset. We just put dot here, and so use columns property of this object. This is a kind of list which contains all columns that we have in this data frame. As we discussed, rows in the table that we have are usually called observations, and columns are usually called variables. And different variables can have different types. For example, age is numeric variable, it contains numbers. And work class is categorical variables because it contains some categories of job for a particular person. For example, state or private and so on. So we may be interested in getting information about types of all variables in dataset. To some extent, it can be done using the following property dtypes. Dtypes report information about the internal Python representation of each variable. For example, age has type int64, which means that it is integer number that takes 64 bits in the memory. So basically it is just integer numbers that can be rather large. And for example, work class is an object. Object is a kind of heterogeneous type of data in pandas. It means that in this column there can be non-numeric elements. Usually these elements are strings. But it is possible that we have in the same column strings and numbers, and all them are called just object. but usually it is not very good idea to store strings and numbers in the same column. Usually it is better when each column has only one type. Now we may be interested in some descriptive statistics of this data set. We want to look at the data and give some general impression about our variables. This can be done using method describe. As you see, this method gives us a new table. This is actually again a data frame, but in this data frame rows are not observations as previously, but each row contains information about some descriptive statistics of all numeric variables in our data set. For example, here for age, we see that the mean value of age is 38, and standard deviation of age is 13, and minimum value is 17, and so on. Here are also quartiles, so this is median, this is first quartile, and this is third quartile. And finally, this is the maximum value. So we have just usual descriptive statistics for numeric data. If we are interested in non-numeric data, we have to pass a special option include equals to O. O here stands for object. And in this case, instead of reporting descriptive statistics for numeric variables, we have descriptive statistics for non-numeric variables, which are object variables. Here you see, for example, that for work class you have 8 unique values, so 8 categories for this variable. And the most common category is private, and this number is frequency of this most common category. In the same way, we can find that the most popular education is HS grad, and we have 16 different levels of education in this data set. So this allows us to get some general impression about the data set. Now, if we are interested, for example, in particular levels of, for example, this work class, we can use method unique for the corresponding column. First of all, we have to select this column. This can be done using these square brackets. And when I put the name of the column, I get the column itself. And then I can apply different operations to this column. So if we wanted to get all unique elements in this column, we can use this unique method. And this is all levels of our variable, all categories that are written into this variable. You see here that most of these levels are just strings, but there is a special item which is none, which stands for not a number. This is a special value in pandas, and actually not only in pandas but in Python itself. And in pandas, this value denotes the so-called missing or NA. So it means that the corresponding value is not known. And this value needs special treatment, and we will discuss it later in details. It also can be interesting for us to count all rows depending on the value of this variable. So we probably want to know how many persons in our data set work in private work class and how many work in federal and so on. This can be done with method value counts. This gives us information of how many records we have for each value of this variable. So as you see, in this way we can get just basic descriptive statistics of our data set. Now let us discuss how to visualize them. Let me show you how to visualize some information in dataset. Actually, there are a lot of methods of visualization, and now we discuss only the very basic ones. First of all, I will import pandas and load the dataset. We continue to work with the same dataset at LCSV. And then I turn on matplotlib in inline mode, so all figures will be shown in the notebook itself. Now I can use some methods of pandas that allow me to draw pictures. First of all, we may be interested in visualizing some categorical variables. For example, in this variable education, we can count values in this variable. This can be done by value counts. And then we can use this object and visualize it with bar plot. This can be done with this command plot bar. In this case, you see that we have a lot of HS grad people in this dataset, and the second one is some college, and the second one is bachelor's, and so on. This is the bar plot that we discussed in the previous videos. Now, what about numeric variable? We can use histogram to visualize it. For example, we have variable age, and we can use method hist to visualize this age. As you see, we have people from 17 to 90, and there are not so many people of elderly age, more than 70 to 90-year-old, but a lot of people here are from 20 to 40, and this histogram allows us to understand this distribution of ages in our dataset. To make things more clear, we can change number of bins for this histogram. For example, we can increase number of bins, but in this case we get, in a sense, noisy image, and we can also decrease, for example, 20 or 10 or 5 bins in our histogram. Another way to visualize the distribution of some numeric variable is to convert it first to categorical variable. For example, we have our variable age, and we may be interested in several groups of people of different ages. For example, we may be interested in grouping people who are less than 30 years age to one group, and between 30 and 50 to another group, and more than 50 to the third group. This can be done using pandas function cut. which allows us to convert numeric variable into a categorical variable. For example, I can say that I want to convert age into 3 categories. And the endpoints, the borders of these categories will be 0, 30, 50, and 100. And we can give some names for these categories. For example, young, major, senior, and then we have a new column which is not included into our data set, which is just a column itself. We can add it to our data set using command like this, age category, for example. Oops, df. And now instead of age, we can work with this new column age category. And now we can visualize this age category using the same technique as we discussed previously with categorical variables. For example, I can do df age category, value counts, and then I can make a bar plot. In this case, we use bar plot to visualize categorical variable which is created from some numeric variable by this conversion. These are just basic techniques to visualize one variable, but it allows us to get some information about the distribution of values. It allows us to understand which values are more frequent and which values are rare in our dataset. And it is a very good first step to analyze your data. Let us discuss in more details how to work with particular columns and how to convert columns from one type to another. We continue working with dataset adult CSV. Let us consider, for example, age variable, age column. You see that this is a column of integer numbers, and its dtype is int 64. But it is also possible to have some float numbers in a variable like age. And we can convert this column to a different type using method sType. So, for example, we can use the command sType float to convert all these numbers to float type. Now you see that they are not integer, but floats due to this dot here. And the corresponding dtype also changed. Actually, in some cases, this conversion from integer to float is done automatically. For example, if you perform some operation with members of this column, which makes some members not integer. But this sType method is a general method that allows one to convert variables from one type to another type. Again, just this command just returns a new column, but it does not change the initial data set. If I wanted to change the value of this column in the initial data set, I have to make an assignment. like this. Now, if I check the dtypes, I see that age is float, not int. In the same way, I can use a different kind of conversions between categorical variables and numeric variables. For example, we have categorical variable education. And we may be interested in converting this education from strings to some numeric values. As we discussed, this can be done in different ways. For example, we can use a label encoding which just assigns to each category level here a particular number without any particular meaning. And this can be done in pandas in the following way. First, we get our column education, and you see that currently it is an object. As I said previously, in pandas there is a dedicated type of variables which is used to store categorical variables. And we can convert this object variable to a categorical using type category. Actually, the content of this column did not change much, but if you look at the corresponding information about this column, you see that now it is not just an object, it is not just a collection of strings, but it is a categorical variables, and there is 16 levels, 16 possible categories, and here are these categories. Now we can use this new column, categorical column. Let us write it at the same place as before, education. And now we can convert this categorical variable into a numeric variable in the following way. We get this education column, then we put cut. This is a special thing which is called accessor. It allows us to get access to specific methods that are associated with categorical variable. Then after this cut, I can use quotes. You see here the new column that contains numbers, just integer numbers. And each number is a code of a particular category. Let me add this new column to my dataset, education codes. I just use a new name for this column, education codes. And let us look now at the education and education codes. You see that when education is bachelor's, the code is 9. And when education is HS grad, the code is 11. So different categories have different codes. And now we can get information on which category corresponds to which code using the following thing. I get this education column, and I use cut accessor, and then I just put categories property into it. So here all categories are just in the list or list-like object, and the position of each category corresponds to the corresponding category code. So this category 10th has code 0, this category 11th has category code 1, and so on. So here they are just in the order of their codes. And this allows us to use the simplest possible way to encode categorical variables. But if you are interested in something more complicated, you can use some special pandas function to do it also. For example, we can use dummy encoding or one-hot encoding with pd get dummies. This function allows us to construct dummies from some categorical variable. Again, we can use education. And you see that this function returns a new data frame. And in this data frame, each row consists of zeros and ones. And all the columns corresponds to categories, category levels that we have in this variable. And the only number 1 in the row corresponds to the level that our category take for a particular object. For example, for the first row, we had a category of education is bachelor's, and so we have 1 here. The same for the second row, and for the third row it is HS grad. So if I want to add these new variables to my initial data frame, I can use, for example, join command, and now I have these new comments that gives us one-hot encoding for education variable. If I want to get really dummy encoding when the number of new columns is equal to the number of category levels minus 1, I have to provide a special option to this get dummies. Drop first equals to true. So here you see that we don't have column for 10th category because we understand that if we have all zeros here, then it means that 10th have to be 1 and vice versa. If you work, for example, with linear regressions, you probably want this kind of encoding for your categorical variables. So these are just the simplest way to work with columns and to encode them in different ways. By the way, if you have a column, for example, numeric column, and you want to get some information about its particular descriptive statistics, you can also do it in the following way. You can get this column and get, for example, mean value of this column, and then you get just a number that is the mean value of numbers in this column. In the same way, you can get standard deviation, for example, or median, or something else. There are no special function that allows to find interquartile range, but you can find the corresponding value using quantile function. Quantile gives a particular quantile of your dataset. So, for example, this is the third quartile, and this is the first quartile, and interquartile range is just a difference between them. So we can just write it in the following way. This allows us to work with particular columns in our data frame. Actually, this is just the beginning of the story of pandas. We will discuss later more complex ways to use pandas to analyze data frames. At this week, we made a first step in analyzing of data. First, we discussed that in statistics, we usually assume that our data can be considered as a sample from some system of random variables. And our goal is to use data to make some conclusions about these random variables. This allows us to make conclusions, for example, about future observations that are not included into our dataset. For example, to make some predictions. We discussed that data variables can be numeric and categorical. Numeric variables can also be subdivided into real and count, but this subdivision is a little bit non-strict. And categorical variables can be also subdivided into ordered and unordered. There are descriptive statistics that allow us to summarize data. For example, measures of central tendency that allows us to describe, in a sense, typical element of our data set. And there are measures of statistical dispersion that characterize how different objects in our data set are. We discussed that descriptive statistics can be used to estimate the corresponding properties of the random variables that created our data, at least in our model. For example, value like sample mean can be used to to estimate the expected value of the corresponding random variable. Finally, we discuss ways to visualize the distribution of our data. For example, to visualize distribution of numeric data, which corresponds to a continuous random variable, one can use histogram, which corresponds to a probability density function from probability theory. And for categorical data, one can use bar plot. This simple but efficient visualization technique are used all over the practical data science. The main topic of this week is correlation. When we need correlations, let us assume the following problem. We have a data set with two variables, age and income. And we want to predict income for some person with known age. And we know that this age is 37. We can analyze the data that we already have and make the following decision. There are a correlation between age and income, and this correlation is positive. This can be obtained automatically. What does it mean? It means that older people have higher incomes. This is an idea that we can get from the data if we look carefully or if we apply some mathematical techniques. Then we can use this information to make a prediction. And even without any mathematics, we can conclude that for age equals to 37, the income most probably will be somewhere in between 2,000 and 2,500. This is a predictions that is based on data, and it is based on the concept of correlation. We will discuss how to visualize a dependency between numeric variables like was shown on the table before. Then we will provide a definition of sample covariance and Pearson correlation coefficient, which is the most popular way to measure correlation between variables. We will discuss a very important thing, that correlation does not mean a causal relationship. If we have correlation between two variables, it does not mean that one variable changes because another variable changes. It can be due to different effects. Anyway, correlation can be very useful when we solve the problem of prediction. And we can use run correlations like Spearman's correlation or Kendall's correlation for nonlinear dependencies and for improved robustness. Previously, we were interested in one numeric variable. Now, let us assume that we have two numeric variables and we are interested in some relations between them. Let us assume that we have a study that involves some people, and we have two numeric variables associated with every person in our study. For example, we have age and income of each person. So our data can look like the following table. For example, we have 23 here. So we have a person of age 23 and income 1000, and another person of age 51 and income 2000, and another person of age 35 and income 1200, and so on. So we have a lot of rows like this one. First, we may be interested in the visualization of this data. This can be done using scatterplot. In scatterplot, we have Cartesian plane, and on axis we have our two variables. For example, horizontal axis will be age, and vertical axis will be income. Then each point in our dataset corresponds to a point on this plane. So, for example, the first point here is of age 23 and income 1000, corresponds to the point somewhere here. This is the first item of my dataset. And for the second item, I have a point with horizontal coordinate 51, somewhere here, and vertical coordinate 2000. So the second point is somewhere here. And the third point is somewhere here. And so on. I can add more points here and get some picture like this. This picture is called scatterplot. The scatterplot allows us to estimate some regions where we have a lot of points and regions when we have a small amount of points. For example, we see if we assume that this data is correct, we see that there are very few people of age about 51 who earn less than 1000 of their income. So we have no points here. And in the same way, we see that for people of age about 20, we do not have high incomes. These incomes are somewhere here at level 1000 and not at level 2000. We don't have points here. So this scatter plot allows us to say something about the relation between these two variables. Also, this scatter plot is related to probability density functions that we discussed in probability course. Assume, as we discussed before, that our data is a sample from some system of random variables. I will denote my variables now by x and y, just to shorten the notation. So age will be x and income will be y. And I will say that there is a system of random variables that I will denote by x capital and y capital. This is a system of random variables. And I believe that each data point in my data set, so each point xi, yi, is sampled from this random variable, from this system of random variables. And as usual, we assume that different points do not depend on each other. So this is independent and identically distributed sample. It means, for example, that the income of the second person does not depend on the income of the first person, and the income of the second person does not depend on the age of the first person, and so on. So this is IID sample. We assume that x and y are continuous random variables, and moreover, there is a joint probability density function for this system. Then this probability density function is related to this scatter plot. So let P is a joint probability density function. Let us visualize this function by plotting regions of large value of this function and regions of lower values. So I plot again this axis, x and y, and assume that I have, for example, large values somewhere here. So this is level 5, and here values are larger than 5, and for example here I have value 3, and here I have value 1. So it means that here between 5 and 3 the values of my probability density function are between 5 and 3, and here the values are between 3 and 1. So here the values of this function is lower than here, and here it is even lower than here. So this is a so-called contour plot that allows us to imagine this probability density function for two variables. Now, if I sample my data points from this random variable, we will get a lot of points in the regions where the value of this function is large. So we will get points here, and we will get a little bit less points here in this region, and even less amount of points here. and practically no points here. So we see that the scatter plot of a sample that is generated from a pair of random variables with given probability density function is related to this probability density function itself. In the region when probability density function is large, we have larger density of the points in our sample, the points of our scatter plot. Which is quite natural because it is what probability density function means. So we can say that density of points on the scatter plot is approximately equal to probability density function. Now we have a tool to visualize the pair of two variables in our data, and we know the relation between this visualization and probability density function of the corresponding random variables. We see from this graph that we can conclude some relations between two variables that we have. Now, let us discuss in more details what kind of relations we are mostly interested in. Now, we are ready to discuss the notion of correlation between two numeric variables. Let me consider four different datasets. Each dataset contains two numeric variables, x and y. I will draw the corresponding scatter plots. This is the first dataset. This is the second dataset. This is the third dataset. And finally, this is the fourth dataset. Let me enumerate them. 1, 2, 3, 4. Now, let us discuss what kind of relations between variables express each of these scatter plots. Let us begin with scatter plot number 2. We see here that if x is relatively large, so we have the values of x somewhere here, then the corresponding values of y are also large. We see values of y somewhere here. And if values of x are small, the values of x are somewhere here. The corresponding values of y are also small. Our data points are somewhere here. We see that there is a relation between x and y. This relation is more or less monotonic. When x increases, y is also increases. And we can see that this relation is approximately linear. We can draw a straight line that will roughly approximate this tendency, this relation between x and y. Of course, if we select a pair of points we can find some kind of violation of this tendency. For example, if I select this point and this point, we see that here larger x corresponds to lower y. But on average, we have the relation that larger x corresponds to larger y. On this graph, the situation is opposite. If we know some value of x, if we know, for example, that x is somewhere here, then we know that y is somewhere here. But it is the same as if we know that x is somewhere here. So the value of y more or less is independent of the value of x, at least on average. In this case, we can say that there is no correlation between x and y. Now, let us consider this third case. Here we see that larger values of x correspond to lower values of y. In our terms, we will say that there is negative correlation between x and y. Now, let us discuss this picture and this picture. We see that on both pictures there is a positive correlation between x and y. But we also see that here this correlation is in a sense more straightforward. For given x, the range of possible values of y is rather small. And here, for given x, the range of possible values of y is rather large. So we can say that on this picture we see much stronger correlation between x and y than on this picture. Now we have some intuition about the notion of correlation, and we want the mathematical definition of some value that will encode our intuition. So I want to create a formula that will allow me to distinguish between this picture and estimate the strength of correlation between variables. I begin with the notion of sample covariance. Let me draw again a scatter plot like this one. First, I want to find the average value of all x's and of all y's. So the average of all x's is somewhere here. This is x bar. And average of all values of y is somewhere here. This is y bar. Now let me draw two straight lines for these values. I will be interested in the following sum. Sum for all data points of the following product: xi minus x bar times yi minus y bar. For example, if I have this point, the corresponding differences are positive. This is the distance, this thing is distance from this point to this vertical line. This is x minus x bar. And this distance is this distance y minus y bar. Let me assume that this is the point number 1. So this is x1 and this is y1. So we see that in this part of the graph, x coordinates of all points are larger than x bar, and y coordinates of all points are larger than y bar. and it means that here this product will be positive. What about this part? In this part, both differences, this and this, are negative because, for example, here x-coordinate of this point is less than the corresponding x-bar. So this difference will be negative, and this difference will be also negative. And product of two negative values is positive. So these points also make positive contribution to this sum. Let me denote these points with positive contribution by this pink color. What about this point? Here, the difference x minus x bar, this difference is negative. But this difference is positive. So this point gives us negative contribution to this sum, as well as this point. We see that if this picture looks like here, so we have a lot of points here and a lot of points here, and small amount of points here and here. This sum will be positive. But if we work, for example, somewhere here, then the corresponding sum will be negative. Indeed, let me draw x bar and y bar here. And you see that we have a lot of points with negative contribution, these points, and a small amount of points with positive contribution. So for this picture, this value will be mostly likely negative. And for this picture, we see that the number of points with positive contribution and the corresponding products will be more or less like the corresponding negatively contributed points. So these points will give us positive contribution, and these points gives us negative contribution. And we see that they can compensate each other. So we can expect that for this picture, the sum will be close to zero. We see that this sum, in fact, catches the idea of this relation between x and y. If I divide this sum by n, I will get sample covariance between variables x and y. So this is covariance between x and y. To make correlation out of this covariance, I have to divide this covariance by the product of standard deviations of x and y. So correlation, especially Pearson's correlation of x and y is covariance x and y over standard deviation x times standard deviation y. I use the same denominator while calculate the standard deviation as here. So if I put n here, I have to put n in the denominator in the formula of standard deviation here and here. The advantage of Pearson's correlation is that it does not change when x or y are rescaled. For example, if I rescale the variable x and multiply all values xi by, for example, 10. It means that I just change the coordinate system here at the horizontal axis. I just change the unit of measure. Then the covariance will multiply by 10. But standard deviation will also multiply by 10. And these multiplications will cancel each other. So we see that Pearson's correlation does not depend on the choice of units of measure of x and y. It is a rather good property for the correlation measure because we understand that the strength of relations between two variables should not depend on the units of measure of these variables. Returning to this picture, I can say that in this picture, Pearson's correlation is close to 0. This correlation is usually denoted by letter R, and here it is close to 0. Here, when our relation is almost linear, Pearson's correlation is close to 1. But it is not more than 1, because Pearson's correlation is from -1 to 1. So this value lies in the segment from -1 to 1. And the value when r equals to 1 exactly means that we have exact linear relation between two variables. Here, Pearson's correlation is positive, but not very large. It is probably something about 0.6 or 0.7. And here, Pearson's correlation is negative. It can be about negative 0.7, approximately. So, we see that Pearson's correlation, which is usually denoted by R, is a number from -1 to 1 that allows us to measure the strength of the relation between variables. And it works pretty well when we assume that the relation between variables is linear or approximately linear, as on these pictures. For different kinds of relations, we can use different kind of correlations that we will discuss later. Correlation gives us information about the association between two variables in our dataset. But the interpretation of correlation can be a little bit tricky. It is possible to get into the trap here if you confuse correlation with causal relationships. Let us discuss it using an example. Let us assume that I conduct some study and I'm interested in the following question. Are vegetables good for our health? Is it good to eat more vegetables to become more healthy and live longer? It is possible that I collected some data using some kind of surveys and visualized this data in the following scatter plot. On the horizontal axis, I will draw amount of vegetables in the diet of my participants. And on the vertical axis, I will draw some kind of health index. This health index measures in some way how healthy the particular person is. And let me assume that my data looks like the following. Assume that I collected this data and I calculated my Pearson's correlation coefficient for this data, and I get the answer that this Pearson's correlation coefficient is greater than 0. Can we use the fact that the correlation is positive to conclude that it is good for my health to eat more vegetables? So, can we suggest, for example, for our customers to eat more vegetables to be more healthy, using this data as the foundation of our suggestion? On the first glance, it is a good idea, because we clearly see that those people who eat more vegetables are more healthy. But the tricky part is the causal relationship between these two variables. The correct way to interpret this positive correlation is the following. If I pick random person, and I know that this random person eat a lot of vegetables, then I may safely assume that the health index of this person is relatively large. This is what correlation says us. If I pick random person and observe, large amount of vegetables in diet for this person, I can conclude that this person is healthy. So, this interpretation is correct. But note that this is a purely observational setting. We pick somebody random, we observe one variable, and we make a conclusion about another variable. If we want to give an advice, we have to consider a little bit different question. We have to say, if a particular person switch from low level of vegetables in their diet to high level of vegetables, or vice versa, how it will change their index. To answer this question, I have to take into account possible causal relationship between these vegetables and this health index, which are not covered by just this correlation. Indeed, this picture can be explained in different ways. The first way, which is possible, is that the large amount of vegetables is a reason for large health index. So, in this case, we can say that vegetables act on health in a causal way. It means that if I will change my vegetable consumption, I will change my health. This is possible explanation of this picture. But this is not the only possible explanation. Another alternative explanation is the following. There is a third factor, a third variable, that is not included into my study. This variable, for example, can be healthy lifestyle. In this interpretation, our participant first chooses their lifestyle. It can be more healthy or less healthy. For example, if this person chooses healthy lifestyle, they eat more vegetables, but also they do some kind of sport, or they visit doctors often, and so on. So they are interested in their health. In this case, it is possible that healthy lifestyle itself acts on the health index, and as we believe that those persons who prefer healthy lifestyle eat more vegetables, we assume that healthy lifestyle also acts on vegetable consumption. In this case, it is possible to observe the same picture, the same correlation between health index and amount of vegetables, even if there is no any causal relationship between vegetable consumptions and health index. We can say that vegetable consumption in this case is just a proxy for healthy lifestyle, but it does not change the health itself. It just gives us information about the lifestyle. So, if some person do not have healthy lifestyle, for example, they do not visit doctors and do not do other things that are usually do people with healthy lifestyle, and we say them that they have to consume more vegetables, they will increase the value of this variable, but it will not increase their health index, because the reason of a large health index of people who consume more vegetables are not vegetables themselves, but this healthy lifestyle. So this is also possible explanation, which is consistent with this data. No correlation can distinguish between these two possible explanations. So we cannot use correlation to make causal conclusions unless we are assured that there is a relation like this one. And this kind of relations have to be obtained using different tools, not correlation itself. Anyway, correlation is a good measure of association between variables, but we have to understand that this association is of observation nature. If we do some kind of machine learning and we are interested only in predictions, we want to predict the health index, and we use information about vegetable consumption. And we know that there is a correlation. We can use correlation to make these predictions. But if we want to interfere, if we want to make decisions like what parameters should we change to achieve a particular goal, we have to make a more complicated causal analysis. Anyway, correlations are important when we are interested in the association between two variables. But Pearson's correlation that we discussed before is well suited for linear relationship. Now let us discuss nonlinear relationships and correlations that are suited for them. Pearson's correlation that we discussed so far is a very useful tool, but sometimes different kinds of correlations are more appropriate. They are called rank correlations. Let us consider a couple of examples where rank correlations are better than Pearson's correlation. First, let us consider the following data set. Here you see that there is more or less perfect correlation between these two variables in the following sense. If x is larger, then y is also larger. But the relation between variables is not linear. And in this case, the correlation coefficient, Pearson's correlation coefficient, will be less than 1. So we see that despite the fact that we have, in a sense, perfect dependency between x and y, the Pearson's correlation coefficient is not equal to 1. It is less than 1. So Pearson's correlation coefficient cannot catch the idea that this kind of dependence is also, in a sense, perfect. This is one possible problem. Another possible problem is outliers. Let us consider another example. Assume that my data set looks like the following. If we look at this part of the picture, we see here strong positive correlation between x and y. But if you consider the whole data set and find Pearson's correlation coefficient, this coefficient can be low or even negative, because this point can add some negative term to the correlation coefficient that can be very large. Its point is far enough to the right and to the bottom. This point, in fact, can be just an error of measurement. So probably we want to ignore it, but it is a better idea to use a statistical tool that is not sensitive to such points, to such outliers. And rank correlations can deal with this situation as well. So, what is the idea of rank correlations? The idea is to go from the initial data set to a data set of ranks. So let us discuss ranks. Let us assume that I have some sequence of numbers. For example, 1, 5, 9, 3. Then I can do the following thing. First, I will sort these numbers and get the following sequence: 1, 3, 5, 9. Then we enumerate these numbers. So this is the first number, this is the second, this is the third, and this is the fourth. And I will attach these pink numbers to my original numbers. Then I will restore the order of these blue numbers. In this case, I have 1, 5, 9, 3, and these numbers are attached. Here is 1, here is 3, this 3, here is 4, and here is 2. Then this sequence of numbers is called sequence of ranks of my original numbers. So if I denote this sequence by x, then this sequence is rank of x. So this is the result of rank transformation of sequence x. Note that if I want to compare elements in x, it is the same as to compare these elements here. For example, 5 is less than 9, and here 3 is less than 4. Or 5 is larger than 3, and here 3 is larger than 2. So the order is preserved, but the numerical values are lost. This is what our rank transformation do. Now, how can we use this rank transformation to find correlations? Let us assume that I have two series of values, x1 and so on xn, and y1 and so on 1yn. This will be denoted by x, and this will be denoted by y. Then first I apply my rank transformation to both of these variables. I will get rank x and rank y. Then I will calculate Pearson's correlation between these transformed variables. The result of this operation is called Spearman's correlation between x and y. It is usually denoted by Greek letter rho. Let us apply this Spearman's correlation to our graph here. Let me assume that the exact numbers that we see here form a geometric progression. So if this is x and this is y, then I have the following numbers. For example, x minus 2, y 1/4, minus 1, 1/2, 0, 1, 1, 2, 2, 4. First, we have to find rank transformation of both variables. But we see that both variables are already sorted. So the rank transformation is very simple. Rank x is just consequent numbers 1, 2, 3, 4, 5. And rank y is the same thing. 1, 2, 3, 4, 5. It means that in this case, the Spearman's correlation between these two variables is equal to Pearson's correlation between these two variables. And these two variables are perfectly correlated. And the Spearman's correlation for this set, which is the same as Pearson's correlation for this set, have to be equal to 1. The same situation is here, because our rank transformation ignores the numeric value. This outlier does not affect seriously our correlation, because it is just one point, and the numeric values of x and y coordinate of these points are mostly ignored by our procedure. So this Spearman's correlation